Okay, so first of all, thank you very much, Julien, for this invitation, and thank you for the organizers. As Julien said, I'm Pierre Tandeo. I am an associate professor at engineering school at Brest, so in Brittany. This school is we have two campuses, one in Brest and one is Nantes. It is based on a fusion of two engineering schools, and I'm also a researcher of lab-STICC CNRS lab. So basically my background is applied math, and I did a PhD and different postdocs in oceanography and meteorology. So I tried to use applied mathematics to what we call geoscience. And especially here I will talk about oceanography. So in my talk I have two keywords. The first one is data assimilation. So I will try to explain what is data assimilation, and for me it's a nice example of data science in my field, in oceanography and meteorology. And I will explain why I talk about data-driven instead of model-driven. Okay, so I'm happy to be here because I'm organizing this kind of events in Brest. So I organized, for instance, last summer a workshop and summer school with a very similar topic, okay, data science and environment. So it was the idea was to mix different communities, people from applied math and people from climate sciences, let's say. So about oceanography, meteorology and climate, hydrology. And it was a quite nice event, and now we have some connection with different peoples, and I will talk about this, especially people from Grenoble. I'm also organizing a winter school. It was in January, so we were 5 teachers from Grenoble and Brest and Toulouse. And it was an application of applied math for geoscience. Basically, all machine learning and statistics and probability approaches applied to different problems, real problems in astronomy, in oceanography, in climate. And so this was the first edition in Grenoble, and we plan to have a second edition in Brest for the next year. So as you see, I am organizing this kind of event, and I'm also happy to be here in Grenoble because I'm currently starting a project with a team in Grenoble. So we have different guys here from Ocean Next and IGE, and so this project I will talk about this project because it's very nice to introduce my talk using this context. So it's a project where we provide, my colleagues from Brest, we provide some methodological aspects on data assimilation, and here in Grenoble they give us the data that we will use in this project, and they have a lot of expertise in oceanography. So I think this is a nice, because we are mixing two communities, one from applied math and another from oceanography. So this is an excellent introduction to my talk, to talk about this project. So the context is the following. So I am interested in oceanography, and especially the surface of the ocean. And basically, when we are studying oceanography, we are interested in 3 main variables. So we are interested in temperature, salinity, and the pressure, and this pressure give you the surface currents, for instance. So this is the main goal of this study, is try to estimate as well as possible these three variables at every location and every time step. So the idea is to reconstruct these three variables at a very very high resolution in space and time. So to do that, we can use satellite information. So satellites are monitoring the surface of the ocean, and so we have different instruments on board satellites, and we have instruments to measure the temperature, for instance, here in color. We have also other instruments for salinity. So this is a quite new instrument for salinity. And also we have different instruments, what we call altimetric satellite, to measure the surface currents here in black. Okay. So the problem of spatial oceanography is twofold. So the first problem is that we only measure with satellite the surface of the ocean. So we don't have the information about the depth of the ocean. So this is a first problem. And then another problem is that all these instruments to measure temperature, salinity, and currents, they have very different resolution in space and time and different accuracy. So for instance, the temperature has a very good spatial and temporal resolution. So this is one variable that is very well measured from space. For salinity, the resolution is quite bad and the accuracy of the data is not so good. And for the currents, here the resolution is very, very low at this moment. So one problem of satellite images is try to mix all this information of these three variables and with different accuracy and resolution, and only at the surface. So if you are interested, you can have a look at this animation it will show you the evolution of the surface, for instance, in the Gulf Stream. So this is one data set, I will say, and another data set is coming from the physics. So that's why I call numerical simulation. So we have some physical model to model the ocean. So this is basically Navier-Stokes equation and fluid mechanics equation. So in this equation, you have a consistency between variables. Okay, all the temperature, salinity, and currents are correlated in the equation. So you have a consistency in the variables. And you have to integrate the physical model using computers and applied math to get some forecast of the ocean. So it's exactly the same in meteorology. So in meteorology, you have some physical model that give you forecast for tomorrow or different horizon. So what is also nice in numerical simulation is that we not only get the information of the surface, we have all the information of the water column. So this is an important part, interesting thing of numerical simulation. But what is very useful is to get forecast for the future, and we will use that in data assimilation. So finally, what is data assimilation? And this is the main keyword of my talk, is try to mix the information of the model. So basically try to mix the forecast of the model with, I will say, true satellite observation of the surface of the ocean. And data assimilation is just a link between these two sources of information, and we try to use this information. Here we use statistical method to get a weighted mean between the model and the observation. So this can be represented in a very small scheme like this. So here you have time, and here is the state of your system. So here the state of the system is represented in one dimension, but you have to know that the state of the system in oceanography and meteorology is very, very huge. So this is a problem of data assimilation, is that the state of the system can be very, very important, because we are interested in temperature, salinity, and currents at different location and at different depths. So every time we have to estimate that in practice. Okay, so what we are doing in data assimilation is quite simple. So we are starting from an initial condition here. And what we do in practice is that we apply our physical model to get some prediction for the future, prediction of the state of the system. So most of the time we use a lot of ensembles. So these are different simulations coming from small perturbation of the initial condition. And then we get a spread of our forecast. So this would be the PDF, the distribution of my forecast. And what I'm doing in data assimilation is that I am comparing this PDF with the PDF of the observation. So this is my satellite information at a given time. And what we are doing in data assimilation is try to mix these two PDF. So the result of data assimilation is this. This guy is the analysis. So you see it's a weighted mean of the forecast distribution and the observation at time t. So this is data assimilation. So if you know applied maths, it's like a Kalman filter. So it's a filtering method, and we use specific Kalman filters here. Specific because we are not in a linear case, and we have a very huge size of the state. So we use ensemble Kalman filters. Okay. What I want to say here is that in data assimilation, so that's what people are doing in practice, for instance, in oceanography and also in meteorology. So this is very time-consuming, and you need, I will say, a big team to reach to good results, to good estimation of the state of your system. Because you need some people that are able to run a physical model, which is very, very huge. You need an expertise to run this model. You have a lot of parameters in this model, and it's really a hard task to run this and to run one simulation is very time consuming. Other problem is that also you need a team that knows very well what is the quality of your satellite images, how to deal with satellite data. So you need people from remote sensing, and you need also people from applied math to apply this kind of Kalman filters in very high dimensionality and very non-linear problem and chaotic problems. So when people are doing data assimilation in practice, they need a very big team, and it's a very hard problem. So this is the context of data assimilation. Okay, so now I will try to explain you what we are developing in Brest to deal with the problem we can have in real data assimilation. So in Brest, we are developing a technique. The name is analog data assimilation, and it's it's a technique. The goal is exactly the same as the classic data assimilation. So classic data assimilation is that you have noisy observation of your system, and you will use a dynamical model to get a good reconstruction of the state of your system. So this is the objective. Okay, you want to mix observation and model to get a good to have a good reconstruction of your system. So this is completely model driven, because here we are using model equation to do so. So what we are developing in Brest, it's an alternative. So we don't want to use to integrate the model at each time step. So instead, we want to use historical data sets of your systems. So this historical data set is called the catalog, and this historical data set can come from real observation of your system, or it can come from a numerical simulation of your system. So you can imagine that during the last decades, people were applying models in oceanography and meteorology for a long time for data assimilation, and when they apply the model, they then they basically, I don't know if they keep the simulation. I think they remove the simulation and they don't use anymore the simulation. And what we want to do here is to have a second life of this simulation and try to use that to reconstruct the state of the system. So this is why I call that data-driven, is because I don't use any model equation, and I only use time series to reach to this result. So I will explain you how we can do that and how we can emulate statistically a model using historical time series. So basically, this approach is very time consuming, because you need to integrate your model at every time step, and you have to simulate different different simulation with different initial conditions. So it can be very, very huge in practice. And what is nice here is that if you use just historical data set and you try to learn statistically the emulator, it is very low-cost procedure. So here, maybe you recognize this this equation. So this is a toy model, very famous toy model developed by Lawrence in the 60s. And so this is also called the strange attractor, or the butterfly effect. So I will use in my talk this small model just to show you some simple. It's just a toy model, very easy to manipulate. Okay. So how it is working, what we call the analog data assimilation. So first, I would like to introduce the two equations of data assimilation. So data assimilation is just a filtering problem with two equations. So the first one I will focus here is that we have observation. So this is my satellite observation, Y. And I will compare my satellite observation, and I will use this satellite information to infer the state of the system. So this is the goal. We try to reconstruct X, which is unknown, and it is the hidden information of temperature, salinity, and currents, for instance, in the ocean. And so when I will have some information about observation, I will update and try to update the X component. So what we use in data assimilation is also a dynamical equation. So this is where the model is here, M. So we use a model. So this can be a physical model or a statistical model to get the relationship between the state of your system at the previous time and the current time. Okay. So basically, your equations are here, or you can use a statistical emulation of the system. So that's what we use here in the analog data assimilation. So how does it work, a statistical emulation of a system? So here I use a very famous and very old method, also introduced by Lawrence, this guy who produced the strange attractor. And this is called the analog forecasting. So it's quite simple to understand. So imagine that you are here today. So the state of the system, the weather, for instance, today is like this. And what we want to do is to predict the future. So, okay, what will be the weather for tomorrow? Okay. So instead of applying a model to say you the weather of the system will be that tomorrow, we will use a historical data set to get this forecast. So this is quite simple, because I will try to find similar situation of this situation in my historical data set. So I will identify different situations in the past that are close to, for instance, this weather situation. And then in my historical data set, so for instance, I have three records, historical records, and I know what happened, for instance, one day later. So I know what are the successors. So this is at time t, and this is at time t plus dt. And dt, for instance, is 1 day here. So, and then I use the information of these 3 lines to get a distribution of my forecast. So this is the analog forecasting. So this is quite simple. What you need to do analog forecasting is to have an historical data set, quite huge information. If you want to have a relevant historical data set, you need to have a lot of information. You need to apply the k-nearest neighbors, which is a famous algorithm in machine learning, and then we apply some statistical regression between this column and this column. Okay, so it's quite simple. And then we get a distribution like this. So these are some results about these techniques. So it's always applied to the strange attractor in 3 dimensions. So this is a result of reconstruction of the state of the system. So this is here I compare the root mean square error for different approaches. So one approach is, I will say, our method, our analog data assimilation in a straight line, and in a dashed line we use the classic data assimilation. So classic data assimilation, it means that at each time step we apply the physical equation. So when we apply the physical equation, we apply the true model, and so this will be the benchmark. So it's impossible to have a better result than this method, because we use the true equation of your system. Here we are using a data-driven approach, so we are approximating the dynamics of the model using the analog method. So what I propose here is just to focus on one color, for instance, the blue one. So this is the error with different size of my catalog. So if you remember, the catalog is the size of historical. It is my historical measurements. So when I use a lot of information, for instance here, what you will you see that you reach to the same, basically quite the same performance as the classic data assimilation. So in this small example, to summarize, I would like to show you that if we have enough information of historical measurement, we are able to have an equivalence for the model-driven and data-driven approaches. Whoa, 5 minutes. Okay. So another method that is important is in data assimilation. I will maybe skip this part, but just I will try to show you the impact of what we call the covariance in data assimilation. So when we try to reconstruct the state of the system, we have two noises that are very important in data assimilation. So this is this noise Q and R. So Q is related to the noise of our forecast, and R is the noise of our satellite observation. So in practice, it's very hard to know what is a good error of the model and of the observation. And if we use good Q and R, we can get very good results of reconstruction. And if we use bad Q and R, we can get this kind of reconstruction. So this is really a key point of data assimilation. So if I come back to my model in data assimilation, you see that Q and R, which are my two covariances here, so they are controlling a Gaussian and additive noise in my two equations. So basically, it's quite simple using statistics to estimate Q and R using, for instance, a maximum likelihood approach. So this is what we have done here in this method, CEDA. So we use expectation maximization algorithm. So this is quite common in this state space model, but here we applied this methodology to very nonlinear problem and chaotic problem. So this was published here. So I will just rapidly show you some results. So this is estimation of Q and R, and it's working correctly. So to conclude, I will come back to my project that I have with my colleagues from Grenoble, and this is a first result of method 1 and 2 that I have mixed together, just to show you what we can do with these two methods. So here I'm interested in interpolating satellite images of temperature. So this is given by infrared satellite. Here you can see that all is white is due to clouds. So we have a lack of information in this place. And we want to interpolate the data like this. So I use 40 years of satellite images like this, try to learn my statistical model on using this images of temperature. And here I show you very quick results. So as I said, I try to emulate my model, but my model is only for the sea surface temperature. I only use this variable. And also I try to understand what is the error of my statistical model. So the error of my emulator is here, and the error of the observation is here. Okay. So I will not go into the details because I have 2 minutes. So this is a first result and about this project. So to conclude, and I agree with the previous talk, is that everything I have done in research, I've tried to put it in my GitHub page. So I think it's very important to now to give the code, and it's a very generic code that can be useful for different fields, I think. So as I said, it's completely data driven. So it means that we use historical data set of both observation and simulation to do some data assimilation. and it's quite easy and fast and flexible compared to model-driven data assimilation. So remember that in model-driven data assimilation, you need a team to make some forecast, another guy from remote sensing, and another guy from statistical approaches. And here it's quite simple. I think one guy can do the job quite easily. Okay, so so the perspective of my talk is the following. So I have some perspective about methodology. I will not go really into the details, but there are some. When we want to have an emulator of the dynamics of different systems, so we use a time series of different systems. And so now there are some very nice techniques to transform the time series into what we call an attractor in physics. And this is, I think, a key point of this methodology. Try to transform this information, time series information, into a physical physical space. So this is one important point. And also, I think that maybe in different fields, in ecology, for instance, biology, there are some very high nonlinear problems, and where maybe the model are not very efficient, and maybe you have a lot of simulation data or historical data set of your system. And I think in these cases, maybe this method can be useful for you. So that's why collaboration are welcome. So this is the references, and a nice picture of my campus in Brest. So we don't have the mountain, but we have the Atlantic Ocean. And maybe for the future, we'll try to organize data science in the Atlantic for the for the next year. So thank you very much, and if you have any question, do not hesitate.